How you doing? I'm Mr. Rose, and today we're going to talk about linear motion and specifically center of mass. So to start, we're going to ask that age-old question that I know a lot of you have been thinking about to this point. That question is, how is a baseball flying through the air any different from a hammer flying through the air? And this is inspired by a wise man. His name was Patches O'Houlihan, who once said, if you can dodge a wrench, you can dodge a ball. Now that has nothing to do with anything we're talking about today, but I like Patches O'Houlihan. Anyhow, you can see behind me that I have right here is a ball flying through the air under that nice projectile motion, which means it's flying under nothing except for the influence of gravity, can't speak, and it follows this nice parabolic path. Nothing that we haven't seen before. It's something we've analyzed a bunch of times to this point. Now, if I look at this picture, you see a hammer also flying through the air, and we should see some similarities. We should also see some differences. One, if you notice how complicated the motion is on the hammer, right? The handle's down here, the handle's up here, the handle's down there. Look, I happen to have a hammer, and hopefully we can see this. I tried this a few times without dropping it and getting it on camera. Not sure. Ah! All right, well, that demonstration ended, but we could see, I'm hopeful, that it has that nice complicated path. But you may have also noticed that there's a spot on the hammer that doesn't move around like that. There is one spot that's concentrated that really the rest of the hammer tumbles around. That's the motion that we're going to talk about today, and that center of mass. So the similarities and the differences are, well, the hammer does travel in a projectile motion, but it's kind of a complicated projectile motion, right? It's like only one portion of that hammer has that nice parabolic path. And that portion is the portion that we're going to talk about, right? So the hammer basically flies through the air about its center of mass. So what the heck is the center of mass? Well, a center of mass, which I'm going to abbreviate COM as standard. The center of mass acts as if a system of particles, so to speak, is all concentrated in one spot. Everything is going to travel around that. So we're going to define it as, let's see, I'll say the system of particles that travels as if, one, all of the system's particles were concentrated in that spot. And there's a 2 that goes along with it. 2 is going to be as if all of the external forces are also acting on that one spot that we're defining as the center of mass. So I'm going to start kind of simple. It's always easy to start simple. Let's start with just a system of particles, like a few particles. Let's start system of 2 particles. All right, so we're going to put them on an XY axis. So I'm going to draw my plane here. Let's put a Y there. Let's put an X there. And let's be nice and simple. I'm going to put M1 right at the origin. I'm going to put M2 some distance away, M2. And I'm going to put the center of mass arbitrarily. Let's put it right there. We'll call it X center of mass. Right about there. Hopefully we can see that. And I can tell you, or we can define pretty simple, that particle 2, or mass 2, is some distance away from that origin. Right? That's nice and easy. And if I only have 2 particles like we do here, I can summarize that, or I can find my center of mass about that x-axis. I'm going to say xcm is equal to, well, however big particle 1 is. So that's mass 1 x1 plus mass 2 x2, how far away x2 is, divided by the total m1 plus m2. Or I can summarize that, I suppose, to be m1 x1 plus m2 x2 divided by a total mass m, where m is obviously m1 plus m2. Well, we can see here that if particle 1 is at 0, particle 2 is at some distance away, that means I'm really kind of defining x1 as 0 and x2 as d, the distance away. What if I'm not that simple? What if we have something that's just a little bit more complicated, like a more general, I guess. We'll call that a more general picture. So let's redraw my picture. I'm going to redraw my y-axis, my x-axis, except this time I'm going to put M1 not at 0. Well, M2 is also not at 0. This time I have some distance. X1 is at some distance away. That means X2 from the origin is at a different distance away. And now, well, my center of mass about these two particles, I guess is still going to be somewhere there. And my center of mass about the origin there, that would be X center of mass. But now my distance D in between those two particles, haven't used this purple one yet, D is the distance between particle 1 and particle 2. So here, my difference, I could still use the same equation, but now I would have different formulas. I would have an x1, I would have an x2. So I would not a different formula, a different substitution in. So this would be a nice simple case if I had, I don't know, 1 particle, 2 particles. What if I had a lot of particles? Like 3, 4, 5, 6, lots and lots of particles. I don't know, maybe n number of particles. So if I had, make sure I'm on camera, if I had n number of particles, what would that look like? I need a general formula. So now my x center of mass is going to be, remember, I can say instead of m1, m2, I can just say 1 over the total mass m times the sum of all my particles from I equals 1 to n number of particles of however many masses I have, and however many distances I have. I can obviously expand this into the x, the y, the z formula, right? I could have z here, I could have y there, that doesn't matter. We can expand that into all the directions I want. But we can also put it into a vector form. I know we love vector form. So if I had a general form, right, like a, let's remember that vector r could be x in the I hat plus y in the j hat plus z in the k hat. So if I'm going to expand this all into my vector components, then I would want the center of mass for r, which would be x center of mass, remember COM in the I, plus y center of mass in the j hat, plus z center of mass in the k hat direction in my nice vector form, which means instead of x center of mass here, I really have r center of mass equals, it's still 1 over m because m is just m, but still 1 over m. We're still taking the sum of all of my parts, I equals 1 to n, now of m, I, but instead of x or y or z, I would be in the general form for vector. So this is my most general form. Now I know what you're thinking to yourself. You're thinking summations. If I see a summation sign, I should really think a little bit further than that. I should think like, what if I had lots and lots and lots and lots of particles about some solid object? You thinking calculus? I'm thinking calculus. We're going to think some calculus. So to do that, we're going to need to make some special rules here. So some of our special rules, if I have a lot of particles, like tons of particles, into this wood solid object, that means I'm going to do things like treat. I'm going to treat this as if I had a continuous distribution of particles. Well, what do I mean by continuous distribution of particles? That means I can have a differential particle unit. Now, I don't like differential particle unit, like a differential mass unit. We've done that before, like a very, very small mass unit of dm. So we can take that differential mass unit, that dm, and we're going to sum them all up. And as that word, sum them all up, we're not going to take the simple summation sign. We're going to use some calculus. We're going to integrate every single one or take an antiderivative. So in general, right? Here's my nice general form in the x direction and the y direction, where I'm summing them all up, but we should know, looking at this, wait a second, I've got an x and I've got a dm, and those two things don't match. So we're going to have to mess around with it. That becomes a little bit of a problem, right? So essentially, we're going to take this and we're going to start to play with it, right? And the way we're going to play with it, we're going to think, uniform mass about the x or about the what can I do? What does uniform mass mean? Well, a uniform mass really means like a uniform density, so to speak. So when I know I have a uniform mass distribution, we're going to make some assumption to start. We're going to do this. We're going to really means we're going to exploit density relationships, right? So we're going to assume that we have an approximation. We're approximating some uniform mass, which means we're going to assume we have a uniform mass or uniform density relation. How is this going to be helpful to us is really the question that we have to start to consider. Well, this is going to be a question for us because, well, what do we know about density? We're talking about solid objects here. So if you recall, density for any object, right? Well, let's see. What is my density formula? Density is some mass per unit volume. Well, if we're talking about differential masses and differential volumes, that means I can have a differential mass unit and a differential volume unit, right? So my density, mass per unit volume, or my very small density, dm, is a very small dv, right? So this is either my entire object or this is either my very, very small object. This is kind of a trick that we're going to use as we go forward, right? If I look at this, setting up proportionally, m over v is equal to dm dv, that means I can rearrange and I can say that my very small differential mass, dm, is equal to my mass per unit volume times dv, right? That's just a nice simple rearranging. And that means I can find my center of mass with respect to volume, so to speak, right? I'm going to use the same type of formula. I'm going to say that my x about the center of mass is now 1 over volume times the antiderivative of x v. I can do the same thing for y, I can do the same thing for z, and the reason we're allowed to do this is, again, because we're making some assumptions. We're going to say, well, if mass is uniform distributed about my object, then obviously the density should be uniform distributed about my object. We know density is a mass per unit volume. So really putting together everything we know. And this is kind of the weird part. There are different types of densities that we're going to deal with here in physics. We're going to deal with densities that are called linear mass density, surface area mass density, and volumetric, which is the one we just wrote, mass density. So we need to remember things like if I have a volumetric density, that's the one I just wrote. I mean, we know that is mass per unit volume. The other two are kind of weird, and that's given us by rho. Sigma, right there, this is my surface area. And surface area, at least for me, for some reason, is the hardest to conceptualize, but that means I have a uniform mass distribution about the surface area of an object. And then we have a linear mass density, which is given us by lambda. And that means we have a uniform, I should write linear mass. And that means we have a uniform mass per unit length. So that is something that is just long and super skinny area per unit length. These three density units or density relationships are what we're really going to work to exploit. So I have a simple, or I suppose a general example that we're going to use. So here I have a rectangle, and I have my rectangle pre-drawn on my axis. I'm going to start defining things. Now I want to consider that we have this rectangle that has a height of b, a width of a, a thickness of t. You can see that up there. And I want to find the x-coordinate. I want to find the center of mass about the x-coordinate. So things that I'm going to start to define, right? I know I'm going to use this volumetric. I guess I'm going to start with this. I'm looking for that distance, x. I shouldn't say I'm looking for that distance. I'm going to say this portion that I can label dx is moving about the x-axis. That's what we're going to kind of sum this whole thing up, right? I know that I have some volumetric mass density. So about this dx, this very small section of x that I have, I know that dm is never changing. It doesn't matter where this is, that is going to be the differential mass unit that is proportional to the dx. So I'm going to label that dm, which we already know is our density times my small differential volume unit. Well, how do I find volume? Volume is like base times height times width, thickness. We have that times that times that. So I would have B times A times T. Well, my differential volume now is going to be things, well, some things are changing, some things are not changing. My differential volume, I'm going to say dV is equal to the height, that's B, times the thickness, that's T, but dV, this very small part, then I'm going to need times dx, right? So that is my differential volume unit, just like the volume would be B times T times X. We can use this about different things, macroscopically and microscopically, right? Microscopic is going to be this, and that's probably not the best term, microscopic, very, very small. Macroscopic, big picture, we just say, well, density, I guess I can even write it out. In the big version, I would know density is equal to big mass over big volume, which would be our mass divided by A times B times T. So now my microscopic density, or my differential density, right? I'm going to call it micro. But I really mean my differential. That's going to be rho is dm over dv, which is really dm times what we just put down on paper, right? Times my b times t times dx. My b times t times my dx. And now if I'm looking for that center of mass, about that x-axis, this is where things get to be simplified, right? If I'm trying to find x about my center of mass, I know it's 1 over the total mass times the antiderivative of x dm. And look, I've got this dm floating around. So I need to figure out dm from up here. We're starting to sub everything in. My total dm, well, what is dm equal to? If rho is equal to dm over all that stuff, that means dm is equal to rho times b times t times dx, right? So I'm going to say dm is equal to that whole thing in. Let's give it a color, make it pink. So I can say that my x about the center of mass, 1 over m times the antiderivative of x. And now I'm subbing in for that dm. I'm going to sub in rho times b times t. And I'm going to give it about some little dx. That is the direct substitution. And now I know x, now I can take the antiderivative. So what is that going to look like? Oh, I dropped an equal sign. How do I drop an equal sign? X center mass is equal to. So now what is that actually going to look like? So I'm going to say, make sure I'm still on camera, that x about my center of mass is equal to, I'm going to pull out every constant, make things easy. Pull out those constants. I'm going to pull out a rho, I'm going to pull out a b, I'm going to pull out a t. I know it's divided by the total mass, m, times the antiderivative from x, wow, that's just really easy, x dx. Where am I taking the antiderivative from? I have an indefinite integral here. I'm going about the x-axis from 0 to a. So I need from 0 to a. And now I can take this super simple antiderivative, x about the center of mass. So where's the center of mass about the x-axis? My constants stay the same, times x squared over 2, that's my antiderivative, from 0 to a. And then as I integrate that, I'm just going to, right? So now what I just took the whole antiderivative of that simplifies to a over 2. And rho, well, what I know what rho is. Rho, by definition, is mass per unit volume, which is my MB m divided by a times b times t, which means that my entire expression is technically rho times bt over m. When I sub my rho back in there, this whole thing is going to end up canceling out, right? Because technically, by definition, rho is equal to mass per unit volume, which is a BT. I dropped my A way up there. I didn't drop an A in places, right? When I plug that back in, all of this cancels out, and now I would be left with my X about the center of mass. That's off the camera. What I would be left with is I'm subbing that back in. I'm going to be left with 1 over A. Everything else is going to cancel. BTM, BTM, all of that cancels out. I'm going to be left with 1 over A times A squared over 2, which means my center of mass is at A divided by 2. So for this cube, my center of mass about the x-axis is just at some distance A divided by 2. That is pretty much all I have to talk about today. I hope we followed through that example. I know it was a little bit. That's all I have for you today. Next time you see me on screen, we're going to be talking about the center of mass the center of mass of a uniform density versus a non-uniform density. So that should be fun. Please feel free to like, comment, or subscribe, and I will see you next time.